All right, once again, good morning, everyone. Welcome to the guest speaker series for February 15th, 2023. Today we have two great presentations for us to listen to. My name is Jessica Brooks. I'm from Central Region STI, and I'm going to be hosting the presentations today. So again, I said we have two presentations today, the first of which talking about elevated convection. We've got four great presenters today. Brett Borkart from WFO Chicago, Paul Schlotter from WFO Boulder, Russ Schumacher from Colorado State University, and Keith Sherburne from WFO Rapid City. Our second presentation will be Scott Lincoln from WFO Chicago, talking about determining the location of the May 22nd, 1855 Chicago area tornado. So again, two great presentations today. We're looking forward to it. So with that, I'm going to say a couple logistical things as we go through the presentations. If you have any questions, please put those questions in the question box and we will get to them at the end of each presentation. We will do Q&A at the end of each presentation today. So there will also be opportunity for you to just raise your hand and bring forward your questions in that Q&A time as well. But again, if you have a fleeting thought, go ahead and put it in that question box and we'll get to it later. So with that, I am going to pass the baton on to Brett and let them get started.
All right, well, good morning. Thank you, Jessica, and thank you everybody for joining us today. We realize it's busy across really the whole country with all sorts of different hazards, winter weather, severe weather, and in the Chicago area, at least wind. It's a howling wind outside my window today. So thanks for joining us to talk about elevated convection, a really exciting topic. Really excited to have Paul, Russ, and Keith here today to talk about this. So let's get started. Elevated convection, what is it? Well, most of us are familiar with it, and it's a convection for which all the influence of the updrafts originates from above the near surface stable layer. Now, the most common severe weather report type with elevated convection is damaging hail. That's hail that measures greater than 1 inch in diameter, with a secondary common report type of damaging surface winds, of course, winds greater than 58 miles an hour. Now, 80% of nocturnal damaging wind events occur with thunderstorms along or on the cool side of surface boundaries. And taken together, they come as a surprise. There's a general perception that elevated convection cannot produce damaging winds. Reason being, the idea is that there's a surface stable layer close to the ground that acts as a cushion to prevent downdrafts from reaching the ground. How many times have you written in an AFD or read an AFD that talked about needing to punch through the stable layer, or the stable layer is going to prevent downdraft penetration? So the fact that in at least the climatology of elevated convection, 36% of all reports are associated with damaging winds is a little bit surprising. And it is worth noting that some presumed elevated convective systems, especially those that start at the beginning of the nighttime hours, are likely still surface-based, especially if they have a cold pool that can lift the surface stable layer. So that probably accounts for some of the damaging wind reports in various climatologies. But over the past few years, and especially the past 6 months, our group has identified a growing number of cases with equally spaced elevated convection that is associated with damaging surface winds. And we have a few examples on the right-hand side here. First example out of Michigan with 2 bands of elevated convection. The second example looks like it's Kansas there with 3 bands of elevated convection. If you zoom out, there's actually even more bands. And what's really interesting is with these bands of convection, radar demonstrates a really unique signature with heightened base velocity values well ahead of the leading edge of reflectivity, and sometimes a rapid drop off in the base velocity as the reflectivity moves overhead. And sometimes the radar also demonstrates a divergent couplet, as you can see in the bottom example from near Kansas City on May 4th of 2020. It looks like a pure divergence there close to the ground. And this signature we've noted is present across different storm modes with elevated convection, ranging from supercells to linear storm modes to even single cells. Though across all of and within our growing case list, the majority of cases have more than 2 bands of linear convection and often arcing bands of convection. And anytime we think of bowing lines of convection, a lot of times we think about rear and flow jets, right? That bows the convection out. Well, what's really interesting is that the damaging winds appear to be separate from the momentum of the storm itself. And what we mean by that is that there's no signs of a downburst or descending rear and flow jet. So if we look at this example here, this is from near La Crosse in 2014. You can see the base velocity signature ahead of the reflectivity passing over the radar. The white dot is going to be the La Crosse ASOS. We're going to look at observations in just a few seconds here. And you can see the cross section taken orthogonal to the motion of the storm right as the base velocity feature moves over the radar. And notice that while there are signs of maybe a rear inflow jet with this system, the flow near the surface appears completely disconnected, with even evidence of the stable layer between the rear inflow jet and the ground. You can even see evidence of gravity waves or waves at the very end of the loop there. And what's interesting is the damaging winds occur with a jump in a surface pressure, a change in the wind direction, but little to no or even a modest increase in the temperature. And we can see that with the observations from La Crosse Regional Airport. The pressure's in orange, the winds are in black and gray, the wind direction's in blue, and the temperature is red. You can see the winds and the pressure are highly correlated. The wind direction actually reverts back to the ambient direction after this wind signature moves overhead. This is a pattern that is quite atypical with cold pools or downburst, and instead it's consistent with the passage of gravity waves. And to hit that point home, we're going to look at a couple panels here. The bottom panel is still our La Crosse Regional Airport from 2014. The top panel is a time series from Aurora Municipal Airport from the 2020 derecho. I think we can all agree that was a surface-based rear inflow jet downburst-driven system. And you can notice that, yes, there are some similarities, but with gravity wave coincident damaging winds, the pressure often oscillates, the wind is correlated with the pressure, and the wind direction also reverts back to the ambient direction. And of course, the discriminating factor is the little to no change in temperature. So what are gravity waves? Well, gravity waves are oscillations that are driven by buoyancy. And I think a lot of times when we think of gravity waves, we think of bores and solitons and solitary waves with convection, and those typically develop when the gravity currents such as a cold pool or a cold front lifts a surface stable layer. Topography can also lead to the generation of bores and solitons as well. Another common class of gravity waves are just called mesoscale gravity waves. They're a lot more common and actually have a much larger spatiotemporal scale. The way that these develop are actually, it's an atmospheric response to, it's kind of a mouthful here, but a flow imbalance in a curved jet with rapidly strengthening baroclinic systems. They're actually extremely common, and they're well documented starting in the 80s and 90s, and it's really been in the literature for a number of decades. But the general idea is that the atmosphere will produce gravity waves that propagate vertically with rapidly strengthening baroclinic systems. If those gravity waves get trapped beneath some sort of ducting layer, let's say an environment with strong low-level wind shear, they could actually propagate for hundreds of miles. And gravity waves and convection are known to coexist, again, since even the 80s. And a quick diagram here showing the process where they can actually mutually benefit each other. It's a process known as ducted wave CISC, that's conditional instability of a second kind. The general idea is that a gravity wave will produce low-level convergence, upper-level divergence to the convection, while the convection will produce latent heating to support the gravity wave. It's a mutually beneficial relationship, and the telltale sign is correlated pressure and wind perturbations at the surface. So the question is, how often does this happen? Well, initially, we started collecting cases anecdotally through operational experience. We wanted to do a more systematic approach into identifying cases. We have a whole method where we identify cases, but in the past 2 years, we've identified 49 convective events with gravity wave coincident convection. When we add in the additional cases that we know anecdotally to the additional 8 cases, we're aware of 57 different convective events, elevated convection, coincident with gravity waves. What's remarkable is over half of those events are associated with damaging surface winds, and a quarter of all events, roughly half of all damaging events, are associated with significantly severe damaging surface winds. Which is pretty shocking. And most of those, again, occurring within the past 2 years. So this happens all the time. Take a very quick look at the early climatology. So we're only going to be looking at 2021 to 2022 here, so we don't skew the data with the additional 8 cases that are no doubt damaging. The majority of cases often occur during the springtime months, and that makes sense if there's a dependence on synoptic scale gravity waves. They can occur during any time throughout the day, but they're most common during the overnight hours, which again makes sense. Prevalence of a surface stable layer. But what's really interesting is these events are often long lasting, crossing multiple states, lasting longer than 6 hours. Now, when you break out the climatology from non-damaging, damaging, and significantly damaging events from the time of year or time of day, there's really little to no signal, but there is a signal between the duration, with damaging and significantly damaging events often lasting much longer than non-damaging events. And what does this look like from a regional scale? We do have a radar loop here. This is from a gravity wave event in 2018 across the upper Mississippi River Valley and Great Lakes. You can see evidence of bands of convection moving from the Dakotas all the way into Michigan. The band of convection that moved across southern Minnesota was responsible for wind gusts over 80 miles an hour, quite a bit of wind damage. The bands that moved over Lake Michigan produced a meteor tsunami in Ludington. It completely submerged breakwaters and piers, did a lot of damage. You can see gravity waves also moving across the Dakotas. And looking at the archive surface map from WPC, I know it's a little small on the screen. All the convection was located well north of a surface stationary boundary and to the northeast of a rapidly deepening surface low pressure system. So this system was about as classic as it gets. Now, in terms of where we observed these events happening, again, just in the past 2 years, I'm going to highlight all the radars that have sampled gravity wave coincident convection or gravity wave driven convection. And you can see this could happen anywhere from coast to coast, as far northwest as Washington State, as far southeast as the Gulf Coast. It's not specific to a certain region or topography or the Great Lakes. It can happen anywhere there's actually convection. And just to hit this point home, I'm going to show a 16 panel of different convective events across the country. They can take all different shapes and sizes. And the rhetorical question I want to pose to all of you is if you could pick which events are associated with severe surface winds. And sure, maybe you can make the argument that events that have higher reflectivity produce damaging winds, and maybe that relationship does hold. What's a little bit harder is actually picking out the events that are associated with significantly severe damaging surface winds. And that's a little more nuanced, with fairly innocuous looking banded convection still producing measured sig severe wind gusts. So this is a really keen operational forecasting and warning challenge. And we have a great lineup of speakers today to dive into this. So coming up next, we're going to turn it over to Keith Scherber, and he's going to talk about one event in particular in South Dakota from a regional view, get an idea of the environment and what this may look like on a CWA scale. Then we're going to turn it over to Paul Schlatter, who's going to talk about one event in particular in 2020, a significantly severe storm that produced quite a bit of damage. We're very lucky to have Dr. Schumacher with us. His group actually modeled that event that Paul's going to talk about, and he's going to talk about the mechanism that we believe is responsible for the damaging winds. And after that, I'll close it up. So Keith, I will turn it over to you.
All right, thanks so much, Brett. And I just want to give a quick shout out here to Phil Schumacher and Matt Bunkers, who provided some of the cases for us as we've gone through this study. So just as a quick background, Brett initially came to me about this radar signature and convective evolution a few years back. He had observed several of these cases, some of which he showed here already while working in the Great Lakes region. And he was curious to get my thoughts on them. Having not worked one myself at the time, I thought, this is really interesting. I wonder what's going on. But I didn't have much else to contribute at that time. Well, sure enough, fortuitously, such an event occurred in the Rapid City area last year during the overnight hours of May 11th and May 12th. And this case from last year across western South Dakota is what we would probably call a more typical event of our sample thus far, compared with the case that Paul's going to dive into shortly, which seems to be on the higher end of impacts. But in this case, at 0Z the evening prior to the event, a 500 millibar trough can be seen located upstream over the Great Basin with an associated 60 to 80 knot jet on the downstream side of that trough approaching the Black Hills at this time. The surface chart around the same time shows a post-frontal environment in place over western South Dakota, consistent with what our anticipation was of elevated convection that night. So the SPC's convective outlook from the prior afternoon did include a marginal risk across much of western South Dakota, had both a 5% wind and hail risk. But from working that day, the expectation, as Brett was saying, in operations was for elevated convection and potentially supercells during the overnight period, but primarily a large hail threat. Now jumping ahead to 6Z, the SPC Mesoanalysis at this time suggested very little mixed layer cape across far western South Dakota. You had a single 100 joules per kilogram contour there over portions of the Black Hills. A 6-hour forecast sounding from the 0Z HER on the right was generally consistent with those mesoanalysis fields, showing essentially no mixed layer cape, no surface-based cape, but there was over 1,200 joules per kilogram of new cape at that time. You'll also note the very strong shear in the wind profile with a large looping hodograph there indicative of warm air advection atop that cool post-frontal and nocturnal boundary layer. And I will note that this strong low-level shear is a common feature in the events that we've identified thus far. So jumping ahead, here we have a radar loop through part of the events. And you'll note the inbound outbound velocity couplets evident on the right. I'm going to show a couple still images here after the loop as well. But also observe that as each of these reflectivity features moves through approximately the same corridor, you start to see new reports of either measured wind gusts or wind damage, or even large hail start to pop up. So stepping to the next slide, included on this map are a couple of ASOS locations for which I'm going to show surface observations. The first is the Rapid City Regional Airport, or RAP, in the southwestern corner of the frame. This site received only a glancing blow from precipitation, but was near a local maximum of winds that emanated from that last convective cell around the time of this radar image here. Around that time as well, a 72-mile-per-hour wind gust was recorded by the ASOS. And the second site, as we step forward one more slide and forward about half an hour later in terms of the radar imagery, is Faith, or D07, which was actually impacted by each of these convective features as they moved through the South Dakota plains, albeit a little bit deeper into the lines of precipitation with each of those. And at this time, you see the first of those features starting to move overhead in Faith. And I'll note that wind gusts at this time, and actually throughout the night at Faith, remain subsevere. And we'll see that here as we go into the some of the time series from each of these observation sites. So on the left, starting with Rapid City, we see that prior to the arrival of that main convective feature there, pressure dropped by about 3 millibars, and pressure is in the blue here, followed by an abrupt 4 millibar increase. Now this rise occurred around the same time as a wind shift from primarily northerly, post-frontal northerly winds to westerly winds, and that's consistent with the arrival of the enhanced wind gusts. The peak gusts of just over 70 miles per hour didn't occur until a few minutes later, but that wind shift was the most prominent part of the wind profile there. Beginning around that time as well, we also see a temperature increase of about 10 degrees. So as Brett was noting, sometimes in some of these situations, you may not see much of a temperature difference at all. Sometimes you might see a modest increase. This was actually one of the larger temperature increases, I think, that we've observed so far. At Faith on the right, we find similar pressure, wind gust, and temperature perturbations as each of those convective features moved overhead. Now the timing of pressure rises and falls relative to the corresponding wind gusts appear to change from one passage to the next, but you do see a similar wind direction shift that's roughly coincident with each pressure rise. Again, that's along the bottom there with the wind direction. You go from primarily northerly to, in Faith's case, west-southwesterly, and then back each time one of those convective features moves overhead. Now you'll note that the magnitudes of pressure perturbations are greater here when compared to Rapid City as well. In this case, we had about 6 to 8 millibars of change from each trough to peak, but the temperature and wind speed perturbations were not as significant. As I noted before, Faith's wind gusts actually remained subsevere all night long and actually remained under 50 miles per hour. But in the end, we received several reports of damage with this event as the cells moved through the plains of western South Dakota. Damage through the course of these storms was primarily to farm outbuildings, but note that most of the locations impacted were also very rural between Rapid City and Faith. We do have a pretty good network of wind sensors across the area, largely thanks to South Dakota State Climate Office and also the state DOT. So we ended up with multiple measured wind gusts over 70 miles per hour and actually a peak of 76 miles per hour, roughly halfway between Rapid City and Faith. As a note, we did indeed get large hail with these storms as well. So we did have up to 2-inch in diameter hail observed. And this is another common feature of many of the cases that Brett has identified thus far, either large hail or maybe more commonly a large volume of small hail. Now, before turning it over to Paul, I wanted to briefly touch on predictability of this case using some models that are at our operational disposal. So here I'm briefly going to step through HRRR reflectivity on the left and href maximum wind gust fields initialized at 0Z the evening of this event on the right. Beginning at 5Z, note that we do have some strong maximum wind gusts across the central high plains, is primarily tied to a low-level jet over that area. There are some convective cells across central and western South Dakota in the HRRR at this time, with the strongest near the southern Black Hills. And if we step forward to 6Z, we find that cell has strengthened considerably at this time and is beginning to be associated with an updraft helicity track. Now, you saw earlier that in low levels, the velocity fields appear to be dominated by wave-like velocities, but at higher elevation tilts and as some of these storms started to get farther from radar, we did identify some some rotation evident via radar. These cases might be commonly associated with elevated supercells, as Brett kind of noted before, or the processes that Russ is going to touch on shortly might be somewhat independent of convective mode, because in the events we've identified thus far, some, but not all, seem to be associated with mid-level rotation. So moving to 7Z, that cell of interest is continuing to move off to the northeast. Now it's onto the South Dakota Plains. And note that there are some additional features trying to develop downwind of this main cell in the HRRR. So overall, the radar reflectivity structure looks fairly comparable to what we observed and what we saw earlier in this talk. At 8Z, we see that the track of the storm is overall remarkably similar to that which was observed, and the downstream cells are a bit more mature at this time as well. And we're going to step forward one more time to 9Z, and here we're going to zoom in a little bit. So once there we go. Again, the dominant cell in the HRRR tracked largely along a similar path to what was observed. So from around Rapid City through the Meade County Plains to near Faith, both locations marked on the map here, and then continuing onward into north central South Dakota. I also have a pretty broad updraft helicity track associated with this feature at this time. So it went from a fairly narrow track initially to broadening quite a bit as the system matured and grew upscale. A key feature of interest in the HRF maximum wind gust plot here is a very narrow corridor of enhanced winds, which coincide with that reflectivity feature in the HRRR. Maximum wind gusts here in the HRF did exceed 60 miles per hour, albeit it was over a very localized area. You see the very small area of pink shaded wind gusts there. Now, although we're showing the HRF maximum wind gusts on the right, I can confirm that the maximum wind gusts there in that particular area are from the HRRR at this time. But you'll also notice another narrow corridor of enhanced winds at this hour that could be identified farther southwest, closer to the Black Hills. This was actually associated with the NSSL member of the HRF, which showed a qualitatively similar feature just a couple of hours later. So overall, I think this short overview of some of the cams available to us operationally for this event illustrates that these events can be predictable as long as we know, what to look for leading up to those events. So with that in mind, I'm going to now turn it over to Paul to look at the Akron case.
Yep, thanks, Keith. This was there's no easy way to say it, just a crazy case, something I have never seen before. I hope to never see again, but based on the research that Brett and Keith have been doing on these types of events, we're going to see other events like this. So it's at least encouraging to me to know that other events have occurred, and best yet, when Russ takes over the presentation, he can actually explain the mechanisms, or at least he can model the mechanisms that cause such a damaging macroburst in the middle of the night in early June in 2020. So I was actually working the mid shift. There were just two of us on shift. We were expecting elevated convection, but nothing too significant. The interesting thing was the strength of the cold front and the cold pool depth behind the cold front that was underneath all the elevated convection that we had. I'll go into details on that, but this is by no means the worst of the damage. I just showed three basic photos here. Most of the damage was in a 5-mile swath, and it was roughly EF1 damage was what we were seeing across a good chunk of Akron, and then an east-west road that went east out of Akron. So next slide, Brett. So leading up to the event, I'm going to kind of go in reverse of what Keith did, where he kind of went over an analysis of the event and then the forecast. I'm just going to hit the forecast and talk about what it was like working this event in the office. And then the cool thing is Russ did a really awesome post-event analysis on the actual wind speeds and then the model. So it's all going to kind of flow together. But for this event, here's the day one convective outlooks. On the left is 20Z, and then at 1Z on the right, that 1Z is roughly 5 hours before the event actually occurred. So SPC was also thinking, not a whole lot's going to go on behind this cold front, and you'll kind of see why we all thought that when we get to the surface map. But in general, ahead of that front in the northern plains, there was an enhanced risk, mostly wind. They didn't have anything hatched. The hail and wind threats were both not hatched, but there were 30% contours in that enhanced region in the surface-based Cape zone ahead of the front, ahead and just behind the front that was there. Next slide. So at 500 millibars on the left, there's a pretty good trough for early June. We like that for if we're looking to chase in eastern Colorado, with a strong trough approaching and even digging a little bit with 80 knots on the back side of the trough as it approached Colorado at 0Z. There was a pretty good jet overhead out of the south-southwest directly over Colorado at 0Z. So really good setup for elevated instability and really good shear. We'll say that too. We'll show some photographs in a minute. Next slide. Here is the 8 p.m. surface map. And mind you, this is early June. You check, Brett, I don't know if you can put your cursor top left of the image, Laramie. Yeah, that's 29 degrees in Laramie. This is 8 p.m. in June. So that is a cold front, really especially for June. Northwest winds were already gusting, at least in the center of this image, between 40 and 60 miles per hour. Ahead of that front in northeast Colorado, you'll see temperatures are remaining in the mid to upper 70s with just a light northeast wind, so kind of prefrontal. Plenty of surface-based cape. By plenty, I mean for Colorado standards, it's between 1,000 and 1,500 surface-based cape at 8 p.m. Throughout the evening, though, we knew that cold front was going to just sweep on through, and temperatures were going to drop into the 40s with really strong northwest winds across the entire area. And the cold convection would just deepen throughout time. So we weren't really too worried about anything other than just the winds behind the front without any convection. We figured the elevated instability might be enough for some small hail, maybe borderline severe. Next slide. So because of the high predictability of the winds behind that early summer cold front, we did have a high wind warning in place for northwest winds 30 to 40 gusting to 60 through 3 a.m. on June 9th. The actual event occurred just after midnight in Akron. Next slide. So here are the Denver soundings at 0Z and 12Z, and please keep in mind the event itself, or the storm that caused the macroburst, occurred right in between these two soundings and about 70 miles or 60 miles east of where these soundings were. But at 0Z, you'll see, the front had just moved through. On that Denver sounding, there's a light northeast wind. It would pick up significantly after 0Z as the front deepened. Plenty of speed and directional shear to be had above the cold front, as you can imagine, as the cold air deepened. Lots of turning in the hodograph and strong winds aloft. Then at 12Z, I showed the 12Z sounding. It went up into a weak rain shower, but just showing how deep the northerly flow was. It deepened significantly between 0 and 12Z. And again, the event was at 6Z. Next slide. Got a HER sounding from 5Z at Denver. So just before the storm really got going out near Akron. And just showing again, the cold pool depth is right around at 10,500 feet mean sea level, or roughly 6,000 feet AGL, more or less. You can see it's more unidirectional in the shear aloft, but it does increase significantly. That's a pretty long, straight hodograph above the stable layer there. Next slide. So looking at the MU Cape and SIN forecast from the HER at 4, 5, and 6Z, that red X is where Akron is. I know you can't see it here, but the SIN is super high on every single one of these images because the front had already blown through way before 4Z and it only got deeper. The fascinating thing is some of that elevated instability back, at least according to the HER, backs its way close into Akron. That big rectangular county on the right side that has about 1,500 Cape, that's Yuma County, the county just east of Akron. And it's possible, given the nature of the convection, that ribbon of Cape was actually further west in reality when the storm got going over Akron just around 6Z. It's very possible there was that much instability available aloft. But I mean, we're still talking, it's between 1,000 and 1,500, more or less. Next slide. Checking out the HER max wind gust, showing the front, and the front was way through Akron by this time, so the HER is late. This is only a 4-hour forecast, and it's still pretty late with the front. The front was way southeast of there, and again, the X is Akron. So look, as time goes on, you can notice some interesting convective elements, especially at 6Z, just east of Akron. You'll see some enhanced, thank you, Brett, some enhanced winds forming almost like in a wave pattern. We didn't really think much about it then. Obviously, now that we understand what we're looking at because of the research that this team is doing, the HER actually is kind of picking up on some kind of wave-like structure in the convection. Let's go to the next slide because I zoom in at 6Z. So now we've got her reflectivity showing kind of a gravity wave-like convective pattern just east of where Akron is, with some enhanced winds. The fascinating thing is that this convection, it really just enhanced the northerly flow. It just enhanced the north to northwest winds. When Russ does his analysis, the fascinating, almost frustrating thing was that the extreme winds that hit Akron were not out of the north-northwest. They're actually out of the west-southwest. So almost against the prevailing flow. Next slide. So here we are at midnight. We've been issuing a few warnings here and there for elevated convection, mainly worried about the hail threat. We were trying to see if any downdrafts from the strongest convection actually punched through the cold air and either modified the northerly flow or weakened the northerly flow, otherwise just, messed with the surface flow. Through midnight, nothing had done anything. There was no stopping those northwest winds gusting up to 60 miles per hour. In fact, in Akron, we had a gust to 68 miles per hour just before 9 p.m., just behind the front, not associated with any convection. So this throughout the whole evening, a handful of warnings here and there. Next slide. I'll show the warnings in a minute, but wanted to give you just a setup of what the general convective nature or environment looked like on radar leading up to the Akron storm. So we'll go through this a couple times. It spans from about 9 p.m. through 11:43 p.m. Right at the end is when the Akron storm's about to get going. And I have that in a white oval there. So you'll see this is all elevated. It doesn't really intensify until just before, at the end of the loop here, just before midnight. There is one storm, Brett, if you can go to the north, just south of the Wyoming and Nebraska. Yep, right in there. That storm, we did issue a warning on that. Didn't get any reports out of it, but that one took off pretty well right at the end of the loop. And so we knew there was something going on in terms of convective intensity ramping up just a little bit. And you'll notice right at the end that in Washington County, in the oval, that storm starts to line out just a little bit. So again, keep in mind, underneath that storm, there's northwest winds 40 gusting to 60. These storms above that layer are moving north at about 40. So it's fascinating, the complete opposite directions. Next slide. Just to give, so I grabbed a higher tilt elevation angle just to see how deep that cold air was, and it kind of matched the model soundings, the actual soundings. Everything said the cold air was roughly about between 6,000 and 7,000 feet AGL behind that cold front. Next slide. So what were we doing before the Akron storm? So it's near midnight. I mentioned the deepening cold pool. We didn't get any reports. Obviously, we're getting gradient wind reports behind the front, but no indication that downdrafts are punching through that frontal inversion. We had some small hail reports, nothing 1 inch, mostly pennies and nickels we were getting from the deepest convection across our area. So we were thinking maybe marginally severe. We issued 3 warnings, didn't get any reports. And then we were saying, so right before midnight on that last loop, those storms were intensifying, particularly that one in Logan County that was just south of the Nebraska border, and then the one approaching Akron. For whatever reason, they were intensifying. And then we saw the one line out, and I remember specifically saying out loud, gosh, I'm glad there's a lot of cold air beneath that storm, and it's going in the opposite direction. What are the chances of something punching through that really deep cold air? So that's kind of where we were at this time, not knowing that there were other mechanisms for bringing air to the surface. So these are just the 3 warnings that we issued, the earlier ones on the left. And then we did issue one that did not include Akron. So we issued the warning before the storm lined out. The most intense part of the storm kind of stayed on the west side within that warning box. But as you'll see, the worst part of the winds were to the east of that box as they went through Akron, and we'll zoom in next. So starting with the half-degree tilt, there is our storm lining out and expanding to the east as it goes over Akron. You'll note that it rained in Akron for maybe about 8 minutes, but they got some ridiculously intense winds that Russ is going to talk about in a little bit. On velocity, we were plagued by, at least at the surface, well, First things first, this is 65 nautical miles from the radar. So at that height, the half-degree beam center point is right at 6,200 feet. So we're talking at the best you can see is the very top of the cold layer, the stable layer. The rest is all elevated convection above that. So we weren't seeing any winds anywhere near the surface, and I'm not sure we would have seen much if it was close to the radar because of the orientation of the winds weren't all that ideal, at least until very close to the surface. You'll see in velocity in the top right, it isn't showing a whole lot to hang your hat on as to, oh my gosh, there's going to be a macroburst at the surface. See a little bit of convergence aloft, but it's not great. The strongest wind at any level I found as the storm went over Akron was one single gate of 70 knots, which was still way under what actually occurred. And it was one gate at one particular time at 12,000 feet elevation. So viewing angle bad, far from the radar, just not a whole lot to look at. Next. Here's an all tilts. I don't think we noticed this in real time, but check out right near that X, there's a bounded weak echo region that's not too shabby right along the leading edge of that. Keep this picture in mind because when Russ does his simulation, a very similar feature in the updraft before the winds come crashing down to the surface occurs. So radar was actually able to pick something really subtle up like that. Next. All right, this is right before we go to Russ. So 12:20, after that storm had just rolled through Akron, we started getting phone calls. And we got 3 in a row that were independent, and they were significant damage reports. I mean, they matched EF1 tornado damage as they described it to us. And they were asking if a tornado had rolled through Akron. Well, because of how deep the cold air was, the linear nature of that storm, and the fact that all these damage reports were several miles apart from each other, we were pretty confident to call it a macroburst almost immediately from that, and that it wasn't going to be a tornado. And then I was asking him, because I wasn't the radar operator, but I was taking all the phone calls. And so I asked him, what direction did your tree fall? Expecting it to be, a slight enhancement from the 60-mile-per-hour winds coming out of the north-northwest. Well, the tree fell to the northeast. And so that just kind of floored me. I was at a loss for words. I didn't know what the heck was going on. I didn't know how winds could reverse direction quite like that at the surface and intensify to EF1 type potential. It really changed my outlook on a lot of things in terms of what to look for and what to expect in elevated convection. As Russ is going to go over, there were west-southwest winds over 100 miles per hour that occurred. He's got a full analysis on the equipment that was there. The Akron ASOS actually lost power, so we didn't even know during the event how strong the winds were actually occurring because we lost the Akron ASOS altogether. And Russ had access to some other observations that he's going to go over that are really neat that showed just how strong this event was. We ended up issuing a warning for the rest of the storm as it moved through Logan County, after the fact, after it rolled through Akron. It still generated 60 plus mile per hour gusts as it moved north into Logan County. Ended up being the quickest mid-shift I ever had. Hands down, not even close. I don't even know if I went to sleep when I got home because I couldn't believe what I'd seen and heard. To this day, I'm thankful that there weren't any injuries or fatalities given what this storm did and how unusual it was. So next up is Russ, who's going to give a post-event analysis of the winds and also how he modeled it. Go ahead, Russ.
All right. Thanks, Paul. Hear me okay?
Sounds good.
Yeah, okay, good. Yeah, so, well, you kind of heard the story of this event from Paul there. And well, obviously I wasn't working at the Weather Service, but the next morning when I got up and, fired up Twitter, started seeing pictures of the damage in this area and was also kind of confused because I thought maybe they were delayed pictures because 2 days before this was when that big weird derecho came through, like all through the West and the Great Plains, and I thought maybe they were just delayed pictures from that, but no, then turned out it was from this overnight event and some very impressive damage. And I think Paul showed a few pictures of that, but there were little aircraft flipped over and all kinds of things like that. So similarly, we started looking at this in the same vein that Paul did. Just everything you look at is like, what the heck was going on here? And as it happened, at that time, I was collaborating with Becky Adams-Seelan at AER, and then on a project related to gravity waves and convection, and then had a student, Sam Childs, who had just finished his PhD and was kind of sticking around for a few months and looking for a project to work on. So we started diving into this. So here's kind of a cartoon depiction of you saw the radar loop from Paul there. Here's just kind of a cartoon version of that, along with some of the observations that happened. So in and around Akron here, there were 5 separate weather stations in the area that measured 79 miles per hour gusts or greater over about 3 minutes. The strongest ones from the USDA station about 4 miles east of town that I'll focus on here as we go forward. But also some, this is a coagnet station to the north, 73 miles per hour at 2.5 meters AGL. So not just in Akron, but that's where the worst of it was. Yeah, sorry, you can go ahead now, Brett. And so, start looking at the data, and as Paul mentioned, the ASOS got knocked out. So a lot of the data looked like this, where you see some intriguing things happening and a big wind gust and a pressure surge, and then that's it. So we kind of started looking to see if we could find any other data, and it turns out at the USDA research station east of town, we have some folks we work with there, and they have a couple of Met towers. And so, so you can go ahead to the next one. So they have this is from a 10 meter, kind of a standard Met tower that they have, which kept power through the event and wasn't damaged. And so just some really fascinating stuff in here. This is 1 minute time frequency data. The temperature, so focus, the darker red trace is the 2 meter temperature, or the 10 meter, I guess 10 meter AGL and 2 meters there. They pretty much trace each other. And then the dark blue is the 10 meter wind speed, kind of standard measurements. And so what you see in the temperature, similar to the case that Keith showed from South Dakota, you see the temperature jump up, and then the strongest winds happen just before the peak in the temperature. And then you see the temperature dive down and in kind of a wave pattern, and then it comes back up and then continues. You see 2 distinct periods of really extreme wind gusts. So there's very strong winds through that entire period that you see there. The strongest wind gust of over 50 meters per second, or 113 miles an hour. And then you see the winds drop down, and then you see the winds pick back up. And if you look at the barbs at the top, you see that it's a direction change too. The first and strongest winds were out of the west-southwest. And then the second really strong gusts were back out of the north. So that's pretty fascinating. You can go to the next slide. And then it turns out they also had an eddy covariance tower, and they those tend to collect data at 10 hertz frequency, so 10 measurements per second. A lot of these towers, they don't keep all that data because it's way too much to handle, but it turns out they had it and they kept it. And this is where things get really wild. So this now just covers like a 3-hour period, this whole graph here. The dark blue here is pressure. And so you see that that big pressure spike come up just before the line comes in. So and that's a surge of about 5 millibars in 19 seconds. Well, so there's the first surge that takes maybe 15, 20 minutes of quite a few, quite a big increase. And then that big spike in pressure is like 5 millibars in 19 seconds. And then it plummets down 15 millibars in the next 3 minutes. And you can see the temperature trace wavy through that period as well. So it's all consistent with this gravity wave process. The strongest, wind speed at 10 hertz was over 50 meters per second. And if you convert that to a usual gust, it's like 43 meters per second. And this is at 2.5 meters above ground. So very consistent with what we saw from the other tower, and very, very strong winds. Okay, next slide. So what was happening here? Well, first, I guess what was special about this event, the others already kind of touched on this, but strong winds in eastern Colorado are not common in the overnight hours. Very big peak in the afternoon, like from dry microbursts and usual squall line type mechanisms. the midnight to 1 a.m. bar there showing all the 80 knot gusts in the records for Colorado. All 4 of those in that one bar are from this one storm. So and this also was the strongest measured convective gust that's in storm data in Colorado history. There's 10 reports that are estimated with higher winds, but this is the highest measured gust. Okay, so next slide. Okay, so then we want to try and figure out what the heck was happening here. That was the sort of the goal of this. And so we ran 2 simulations. One, we ran Wharf, kind of a downscaled forecast, a short-term forecast initialized at 0Z. So like ran the model only for like 9 hours and nested down to 267 meters. So we can start to resolve some of these detailed processes. And then a more idealized CM1 simulation down to 125 meter grid spacing that's initialized from the model derived sounding that's on the right there that looks like the HER ones that Paul showed. So very strong low level shear, those screaming winds just off the surface, but a pretty good stable layer there. And so this the simulation results are in a paper that was just accepted in Monthly Weather Review. It's in early release if you want to kind of check out the details, but we'll go through some of the key points here. Next slide. Oh, right. And one thing, these are profiles of different things here, but the main thing to point out here is the lower left. You see the lower left panel. Basically, for gravity waves moving northward, as these convective lines were, there's a critical layer where the wind speed, the storm relative wind goes to 0. And so you might be familiar with that concept, for example, thinking about mountain waves or downslope windstorms. If you ever are trying to forecast for those, that if you have a critical level, it serves as trapping for the waves, and then the waves will tend to amplify underneath that layer. And so that's what we have going on here, which is kind of interesting. So next slide. All right, so here's the Wharf simulation zoomed in over Northeast Colorado and showing the evolution of the convection that developed. So some similarities to the observed radar that Paul showed. The storm's not quite in the right place. It's about a county too far east where the strong winds are. But the contours here are 30 and 40 meters per second, or 58 and 78 knots that you see. So the storm develops this line, it lines out, and then it produces this swath of really intense winds through Northeast Colorado. Again, not in the right location, but the magnitudes of the winds are pretty close to what was observed. And it lines up with the HER runs that Paul showed too, right? We had those kind of wave-like bands in this area in eastern Colorado. So so we think it's getting the process right, even though like as an explicit forecast maybe wouldn't be perfect. All right, next slide. And so if we kind of take a snapshot here, there's 4 different panels at the time when this is going on, zoomed in on the storm. So the upper left is the reflectivity, and then the vertical velocity at 3 kilometers above ground. You see the updraft is way out ahead of where the reflectivity max is, and even the downdraft is ahead of the reflectivity max. That's that bounded weak echo region Paul mentioned. The model is simulating something like that. The upper right is sea level pressure in the colors. So you see that the red area is where the pressure is greatly increased, and so associated with that spike in pressure that we saw in the observations, and also a wave-like pattern, low to the north, and then the band of high pressure, and then the band of low pressure to the south of the line. The lower left is potential temperature and winds at the surface, and then the contours there show where the strong winds are occurring at this time. And so you see there's no sign of like a convectively generated cold pool there. There's cold air from the cold front, behind the cold front, but where the strong winds are, the surface temperature is actually going up rather than going down, and that's consistent with the observations and kind of with this gravity wave point of view. You're bringing and you have a stable air, so you're bringing warmer air down to the surface. And then the lower right is the potential temperature at 2.5 kilometers above ground, and the winds, and then the pressure outlined there basically. So you see this cool band of cool air higher up, and that reflects the wave as well, which we'll see on the next slide. So here's a cross section through there. left side shows the V component of the wind in the colors. So the blue colors are those screaming northerlies that Paul talked about. And then there's southerly winds up above that. And so the air is coming in from the right side of this picture. The black contours are the isentropes, so that's the air is going to be following those lines. The brown colors, if you can see that, are the updrafts, and then the dashed is the downdraft. So you have air coming in from the right here, from the north. It rises up along this wave, and you see the updraft there associated with it. And then it comes in and comes down and crashes down on the other side in the descending part of the wave. So this wave is amplified, and then it's as we'll see in the later simulation, the wave appears to be breaking, and then that's where the macroburst happens. So and you can see the downburst in this image where you have the blue and the red right next to each other. That's the divergent pattern of the downburst, and you can even see like if we looped through this, you'd see an earlier downburst, and that little brown contour there is the edge of an earlier downburst that happened. So the model seems to be, it's a very different process from what you would kind of normally think of in a squall line or bow echo kind of situation producing severe winds. Okay, next slide. And then here's just a trace at every model time step of pressure and temperature and wind speed from the model. And it doesn't match the observations exactly. For example, you see actually the pressure go down before it spikes up, which is the opposite of what happened in the observations, where it went up and then up more before coming down. But you see the temperature spike up. So there's a lot of things that are similar in this trace. And of course, we only have observations from one point, and we can kind of pick these anywhere we want in the model. So it's, there's some sampling differences there as well. But still, it seems to be capturing the gravity wave structure is the main point here, and some of the key features that were in the obs. Next slide. Okay, so then as part of this too, we took that sounding I showed earlier, and figured, well, let's see what happens. We'll put this sounding into CM1 and just put a warm bubble in there, and probably nothing will happen because it's so stable at low levels. So, but well, let's try it, see what happens. Well, it turns out you put a warm bubble in with that sounding, and what you get is something that looks a whole lot like what was observed in this case. So the color shading here is the reflectivity from the model, and then the updrafts and downdrafts and the black contours. And so again, this is just a warm bubble in that weird environment with the strong shear, and we get a line of convection that moves to the north. We get gravity wave type structures, kind of a wild result here as well. So keep looking into this, and the more interesting things we find. So next slide. So in CM1, so now this is pretty idealized. There's no surface friction, but the convection is producing 70 meter per second downburst winds here. So that's like strong hurricane kind of wind speeds. Again, not realistic because of the lack of friction, but it tells us that these environments, when they're there, are actually very capable of producing extreme wind speeds at the surface if you can get the winds down there. So next slide. So here's just almost similar, similar 4-panel is what I showed earlier. And basically the CM1 idealized simulation is showing the same things as we saw in the Wharf simulation, where the updraft's out ahead of the high reflectivity, this wave-like pattern and pressure, the temperature goes up when the strong winds happen at the surface, and so forth. So you go to the next slide. So here's where things, this is kind of the last like animation that we have here. So I'll set this up first before we start looping. So what you're gonna see in the colors is potential temperature perturbations. So the blues are cool, that would be where the upward, kind of the wave is displaced upward. The reds are downward. The black contour shows the strong winds. I can't remember, 35 meters per second. So there, again, there's those screaming northerlies coming in here. And so this is a cross section through the lines. Go to the next one, it'll start looping. And we'll watch what happens here. And we see the wave develop and it amplifies. Okay, interesting. And then all of a sudden the wave breaks and you just start getting these intense downbursts down to the surface over and over and over again in the simulation. So just let this run through 2 or 3 times, because it's I've watched it a lot of times and it's still fascinating. So there's the wave amplifying, basically amplifies and collapses in scale a little bit, and then it breaks, and then you get the downburst. So again, some at least analogies maybe to the types of processes you'd usually think about with like mountain waves and downslope windstorms, not usually with mid-latitude convective systems. So it's a fascinating process, and yeah, that seems, what we can figure out, that seems to be what was happening here. So next slide. And then that's just a kind of a snapshot there from the paper, basically showing that the wave is getting trapped under this critical level, and that's why it's amplifying, and then why you're getting the waves to break. Okay, next slide. And so I think this is, oh, right, the schematic here, this kind of just shows it in a schematic picture. So you've got air coming in from the northwest, rises up over this wave, that air rapidly descends and accelerates, and you get the really strong winds at the surface. Okay, next one. Okay, so we did a similar simulation for that South Dakota case that Keith showed at the beginning. It would not serve great as an explicit forecast, but it produces the multiple convective lines in this wave-like pattern, which is interesting, and some strong winds, nothing like what we saw in the Akron case, but still there. So there's going to be some of the next steps is to analyze this further. And the next one is a kind of similar 4-panel there, basically showing we see some of the same things. The pressure wave pattern is definitely there, and we know it was there from the observations. The increase in temperature when the strong winds happen at the surface. So that'll be the next steps there. I think that's all I've got. Yeah. Yep. All right. So back to you, Brett, to wrap up.
Perfect. Thank you, Russ, and Paul and Keith as well. And just want to hit home, the Akron case was absolutely incredible, and we're extremely fortunate that there's that observation network from the USDA, and very fortunate that Russ and his group had looked at that case. It was kind of funny, they had independently looked at that case, and when Keith and I were preparing an abstract for AMS SLS conference, we saw the poster presentation. We thought this seems very familiar, and we kind of linked up. So very fortuitous. They're kind of operations to research instead of the other way around. But just want to hit home that this is a huge operational forecast challenge. The Akron case, while absolutely extreme, is not isolated. In 2 known cases that we have across the years, the damaging winds were so severe that the National Weather Service, we actually confirmed tornadoes in spite of unfavorable environments and no radar indicated rotation. And I'll just show one example here because it's from my home office. This is, I was 2 years old when this happened, so well before my time. April 19th, 1996, some weather history buffs may recognize this date. It was actually a high-risk day for a tornado outbreak across central Illinois and Indiana, yet one of the most impactful storms was actually elevated along the Wisconsin-Illinois state line. And what was interesting is we had confirmed an F2 tornado in Zion, which is the dot in Lake County, just offshore of Lake Michigan, or onshore, I should say. And what's interesting is in this case, we actually have a unique data set. It was SODAR data set from a nuclear facility that showed the easterly advection of really stable water or wind or temperatures off the cold waters of Lake Michigan. So pretty sure there actually wasn't a tornado, and this was just one point in a swath of extreme winds produced by elevated convection. So these events can pose a pronounced threat to lives and property. And again, they happen at least with some frequency. So just to wrap it up here, hopefully we've convinced all of you, and this is our main goal, that elevated convection can and does produce damaging surface winds. It's not through a process that we traditionally think about with surface-based convection. It's a completely different process. And the process that Russ described, it's sometimes known as up-down trajectories, where you're lifting a surface stable layer and dropping it dynamically. This may not be the only way to get the job done. There's a real cool paper out there from Akron and Parker 2017. They simulated an elevated supercell during vortex and near the Nebraska-Kansas border. And they found that pressure falls within the rotating updraft was actually responsible for up-down trajectories. Though coincidentally, that supercell is actually on the leading edge of a gravity wave packet, so maybe there's multiple things going on at once. But a really important point here, we're not advocating for you to issue a warning every time you see gravity waves coincident with convection. The same thing would go for a supercell. You're not going to issue a tornado warning in every supercell, right? The key here is to use a combination of observations, environmental data, and radar signatures to make informed radar or warning decisions. Unfortunately, the environmental part is not quite there. We're still digging into our climatology, see if we can figure out why some environments produce these damaging winds and others don't. But we do have the radar signature and we do have observations. So what we really encourage you to do is if you happen to see equally spaced or gravity wave coincident convection, that should raise some eyebrows, some red flags, and tell you, hey, I need to keep a very close eye on this and watch observations. If you start getting some really funky wind reports, slap on a warning. It's one of those situations where you just really need to dial in and see what's going on. So what are the next steps? Russ touched on this just a little bit. We want to use our climatology, even though it's just 2 years, it's equal parts damaging and non-damaging to discriminate environments that favor severe, severe, and non-severe events. We didn't show them in this presentation, but we have a few events where the reflectivity is really bare bones, only like 30 to 40 dBz, but still very clearly coincident with gravity waves and did not produce damaging winds. So the question is, what in the environments kind of led to 2 different outcomes? We also want to look at inter-event variability. So Paul had talked about the initial storm near the Nebraska state line that lined out, did not produce any known damaging winds, though in Russ's simulation, it looks like there may have been a little splat. Why was that storm not nearly as severe as the Akron storm in the same environment? Was the cold pool from the cold front too deep there? I don't know. I think that's a really good question we need to dive into. And ultimately, we want to be able to develop methods to forecast severe and non-severe events, especially since these are often severe events, as Paul talked about, but they often occur on the edges of SPC outlooks too, because it's just sort of a different animal that we're not really familiar with. So a final point here, I have a good feeling that some of you on this call have probably worked an event like this before, or at least have seen something like this. Please feel free to reach out to Keith or me. We would love to continue to grow to our known case list. Let us know, and we're gonna have some time for questions here too, but you're more than welcome to email us questions as well. So I think with that, we're right on time here, everybody, and we will wrap it up and open the floor for some questions if there are any questions.
All right, thank you. That was a fantastic talk. Really, really interesting stuff. So yeah, now we'll have some time for some questions. So feel free to raise your hand. I'm sure there are quite a few questions out there. So I will try to unmute you all and I'll call on you and you can go ahead and ask your question. Or again, feel free to put it in the question box and we'll get to it that way. So first, John Stopcotti, we've got you on here. Go ahead and unmute yourself and ask your question.
All right, can you hear me okay?
Yep.
All right. Hey, great talk, guys. I really appreciate this. Really enjoyed looking at the in-depth science going behind all this. Just curious.
I think we may have lost you there.
Yeah, somehow it muted me, I guess. Just curious if there's some precipitation physics that are specific to you know, what's going on with this particular cell, because you know you didn't get, or at least there wasn't reports. We all know how reports are, but especially in eastern Colorado, right? But there weren't more widespread reports, or it was at least pretty isolated to this particular cell. So just curious if in the modeling you're seeing anything on the precip physics side that would allow that that wave to crash right there, or if there's something specific to that particular storm.
Yeah, that's a good question, and we have not looked real closely at that. Because yeah, I think that's a good question. I mean, it's a little bit tangential to what you're asking, but it maybe hints that there are some important you know, microphysical things going on as well. Is that so we originally ran, you know, just basically like a 4-kilometer forecast kind of setup for these. We used the Morrison microphysics scheme and the Thompson microphysics scheme, and the forecast or the simulations were very, very similar to each other. But then going down to this really high resolution, the one with the Thompson scheme produced this nice simulation, and the one with the Morrison was not anywhere near this. You know, it didn't resemble the observations very much at all. So that would, I mean, that's sort of an anecdote that probably microphysics is important here, but how, I'm not sure. It would be something to look more into.
All right, thanks again. I appreciate it, guys.
All right, Scott, I see you have a question in the chat. Do you want to just ask that to Russ?
Sure. So the question I had is I was curious if any of your modeling suggests a rough threshold of the ambient wind speed that would be needed to cause the breaking gravity wave.
Ooh, also a really good question that I don't have the answer to, but I think it's probably more the vertical profile, like the shape of the vertical profile, that's more important than the speed itself. So I mean, in this case is so strange because, as Paul pointed out too, you have such strong winds, such a strong cold front, and that's not super common, but then the quick reversal to southerly winds above it. So yeah, my guess is it has more to do with the shape of the profile, or maybe even the hodograph characteristics. You might view it that way than the actual speed. But yeah, that's a good question. Haven't really quite thought about it in those terms. It would be useful to figure that out, because that obviously would be a useful thing to know operationally if there was something like that. I don't know if you, Paul or Keith or Brett, if you have any, you might have thoughts on that too. I'm not sure from other cases you've looked at.
I mean, nothing to add to what you said there, Russ. I think that's a really good avenue to go into.
Yeah, and just to quickly follow up, I think that'll be one of the goals as we get a larger sample size, as you note here on this last slide, is start to examine inter-event variability, but also try to get a sense of what environments do support these, and what discriminates between those lower end events and the high end events like we saw in Akron.
Because it's also not, it's like, wouldn't even, if I were looking at that, I mean, and maybe, I don't know what the like bunkers motion say would be on a hodograph like we saw in that case. But even just like looking at that hodograph, I'm not sure I would beforehand say, oh, well, if a storm forms in this environment, it's going to race off to the north. Like, I'm not sure that that would even be obvious to, at least in advance. Now, in hindsight, we kind of see that that's what happens. But anyway, yeah, it's a strange environment for sure, but not as strange as maybe we originally thought, as has been shown.
Yeah, and I guess one fortunate aspect of this is, so far based on our case studies and your modeling work there, Russ, it seems like the model can handle the storm motion pretty well. So maybe when we're leading up to these events, we can keep that in mind, kind of use that as a diagnostic for the storm motion, and then assess where the critical level is, what the critical wind speeds would be, and so forth.
All right, so we have another question from Aaron Johnson. Well, I don't know if it's going to let me unmute. Hold on a second. All right, I think we got you, Aaron. Yes, I can. So go ahead and ask your question.
Okay. Well, great presentation. Interesting topic. This kind of builds on a little bit of what John was asking with the precept microphysics. Is there any potential where we're seeing some hybrid combination of gravity wave and even heat burst? I mean, it's not really the same phase. I mean, typically think of heat burst, you think of a decaying phase of convection, but the environment itself, I'm just curious if we're dealing with higher based. Obviously, if it's elevated, it's going to be higher base, but a dry layer. I guess I'm just curious if there is this connection that we're getting this pseudo hybrid of gravity wave plus heat burst.
Yeah, I think that's probably right. There's definitely at least some parallels between them there. They may not originate in the same way, but I think it is there are similarities in the process, right? It's how you've got storms forming above a stable layer, and somehow you're getting getting the air from the warm layer above that stable layer down to the ground via convective processes of some kind. I mean, in this case, it wouldn't have been hot like you normally see in a heat burst, but relatively warm. Yeah, I don't know if the other guys have have thoughts on that too.
Yeah, I mean, I agree with what you said there, Russ, too. And it's important to note with the microphysics question, Keith had noted this, most of the cases are associated with hail, and there's obviously an overlap with elevated convection and mucap and whatnot. There could also be some precipitation drag component to this if you have a lot of small hail dragging air down as well. We do have one really interesting case in southern Minnesota where a dual pole radar would actually suggest there's snow falling. So I think microphysics is an important aspect of this as well. And then, yeah, I think you're right to draw that analogy to heat burst.
All right, so we do have a comment here from Steve Graffiti. He said, great presentation, strength of the unidirectional flow in the elevated, warmer, unstable layer, and the strength of the mesoscale forcing for ascent for convective development in that layer. For example, here, strong PBA with approaching very strong vorticity maximum seem to have been a common factor in some similar cases that he has recalled in past years. Do you have any other comments, Steve, to add to that? I can unmute you and let you speak, or have any of the presenters speak to your question.
No, but can you hear me?
Yes, I can.
Yeah, really excellent presentation. And I think these kind of cases that you've so well presented here this morning have vexed us for years. And I think some of the previous comments, I know Paul and the person just spoke here before me, I think it's probably multiple forcing mechanisms that produce the wind, which is why there's such a difficult nut to crack. And the climatology, again, I sit here trying to recall some of these cases. I know I could come up with a couple of dates, but it just, they're all over the place. But the common thread seems to be getting strong upright convection that persists long enough in a unidirectional wind environment, above that surface layer. And so that you get basically this sloshing event that again, I think you've well demonstrated in at least one mechanism here with the Colorado case and the South Dakota case. But there's probably multiple processes that are at work that communicate that flow down to the ground, and that's what makes it so difficult to come up with a climatology. That there's probably a lot of similar cases, but maybe slightly different processes. And also has been mentioned the precipitation microphysics, but boy, this is a problem that it's big enough. I think we all should be focusing on. I applaud you for documenting these two events, if I'll try to dig up a couple cases off the top of my head here and look back through my notes, but if that would help any. There was a good paper some years ago, you probably have seen it. I think I probably will not pronounce the name right, Bernardet and Cotton. I think it was from a 1989 event that this reminds me of. But basically, it was a sloshing surface flow in response to a gravity wave. And if I remember right, the case wasn't too far from where these two occur, somewhere in eastern Wyoming or somewhere out in that general area in the northern high plains. So, with that environment there is favorable, just like the southern plains, especially for heat bursts, where you get these shallow, stable layers surmounted by layers with steep lapse rates and unidirectional flow. And it just, again, there's just something common, at least ringing in the back of my mind for that kind of environment. And then certainly that part of the world is one where you can realize that setup just because of the geography. So anyway, very good. Thanks for presenting this.
And thank you. And if you can recall those cases, please do let us know. We'd love to have them. And completely agree that there's probably multiple ways to get the job done. And even within the 2 years, the variety in the radar presentation is very interesting, or very curious. In the early season, seems like the bands are further spaced apart. In the heart of the warm season, June, July, where maybe there's less synoptic forcing, the bands are a lot closer together. So I mean, I think there's a lot that really needs to be parsed out here. And I really appreciate your comments there.
All right, so there's one more question. We'll try to, if we can get through this pretty quickly. Brian Squitieri, I'm sorry if I butchered your name, but go ahead and
you
ask
actually said
your
it
question.
perfectly. Can you hear me?
Yes, okay.
Okay, so first off, very nice presentation on a complex severe weather topic. At SPC, we're always watching the CONUS 24/7, and we see all sorts of crazy things, and this is one of those that tends to give us a lot of problems, not just for convective outlooks, but even for MCDs trying to know what to do in real time, because we don't know how long these events are often going to last. However, in talking with some other forecasters at SPC, just looking at nocturnal events alone, one of the things we see to be very common with events like this are very to exceptionally steep lapse rates from 500 millibars going down to 700 or sometimes even 850 across the CONUS. And we were wondering, since you seem to have a good collection of cases, both severe and non-severe, do you think that maybe these very steep lapse rates and their contribution to overall buoyancy might be a key factor for some of these events, particularly the more severe ones?
I think circumstantially, I completely agree, Ryan. Seems like some of the higher end events do have steeper lapse rates. We didn't show this. We showed the map where we've seen these events, but some of the worst events seem like they do happen, like in the plains where you are more prone to having steep mid-level lapse rates. So I think that your observation there and the other forecasters at SPC are onto something there. It's probably a key part of the equation.
Okay, yeah, thank you for answering that. It's just, we've noticed like when you get 8.5, 9.5 Celsius per kilometer mid-level lapse rates, it's like that always leads to crazy things happening at night, both hail and wind wise. And we see that stick out all the time. And so some of us actually tend to lean on that kind of signal a lot for a lot of our nocturnal higher probabilities based events. So we're very curious to see what you guys find out down the road for these kind of events when you start parsing out the environments between the severe and non-severe.
Awesome, thank you.
All right, thank you for the presentation. I think you guys have a lot of work ahead of you. Could come up with some really great stuff. And thanks for all the questions. So at this point, we're gonna switch over to Scott. So get Scott loading his presentation here. All right, I can see your screen now, Scott, so you should be good to go. So again, here's Scott Lincoln. He's gonna chat with us for a little while about locating tornadoes. So go ahead, Scott.
Yeah, so now I have the wonderful thrill of trying to captivate people with a completely different topic. So hopefully if I can just captivate people to the 50% of that last topic, which was amazing, then that'll be good. And as you might have seen on one of the maps that was kind of inserted in one of those slides, that other than just being the senior service hydrologist here at Chicago, I also wear a couple other hats, and one of those is doing a lot of mapping, which will basically play a pretty big role in what I'm about to talk about. A kind of a rather mysterious event from early in Chicago's history, a tornado that did not have a lot of information about it, just that it happened and supposedly was the first tornado ever to happen in Chicago. But beyond that, we didn't know exactly where. So in the next few minutes, I'll talk about that original story, what was the accepted narrative of this tornado. I'll talk about some of the weather records we were able to find, some of the limited pieces of information about the environment associated with the tornado. Talk about some of our new recent research, and then provide a revised account of the tornado. So as a little bit of background, we do frequently receive requests about the number of tornadoes that impact Chicago. I mean, our media are constantly asking, and we get one more little EF0 that goes a couple blocks in the city, and immediately, oh, is this the 33rd tornado that's ever hit Chicago? And where does this rank in the climatology? That question comes up all the time. And some tornado tracks, especially those after 1950, we can be more confident in. They're a little more clear. They were, especially as we get closer to modern times, they were surveyed, and especially as we get really modern, they were put into the DAT, so we could probably be down to the block. But those early tornadoes are much more uncertain, as you might imagine. different sources of information from like the Significant Tornadoes book or some databases that Fujita kept would be really your only source other than, old newspaper articles. So one of the most uncertain in our history is a tornado that happened on May 22nd, 1855, typically referred to as either the Norwood Park or Jefferson Park tornado. It killed multiple people and was one of the earliest known tornadoes in Northeast Illinois. So the original story goes something like this in the Chicago Tribune, which was the, basically until the last couple of years, is the most frequently cited source talking about the tornado, says that there was a tornado that lifted a home off its foundation, killed 3 of 9 occupants, and also produced some fairly large hail. And oops, I clicked the button one too many times. So the events to which we allude took place in the town of Jefferson near Jefferson Mills, 16 miles distant from Chicago. And that really was the only location information provided in the article. So to give a little quick geography lesson as to how that's associated with Chicago, back in 1855, Chicago was a much, much smaller city, centered very close to where the Chicago River outlet into Lake Michigan is located, surrounded by marshland and prairie land, and not a lot of other, villages or towns of significant substance. Outside of Chicago, the county was broken up into townships. So the county, Cook County was broken up, and sometimes you would hear those townships described as town of blank. So for example, if someone was referring to Jefferson Township, they might say town of Jefferson. So kind of keep that in mind, that it's not quite the same as we might say, town of this today, where we mean an actual place of lots of houses and maybe a business district. This can actually refer to a rural place of just farmhouses, known as town of blank. So when someone says town of Jefferson, it can actually mean a couple different things. Back then, there not only was the Jefferson Township, but there also was a very small village near the center of that township, which had a post office, also called Jefferson, just to make things even more confusing. In 1889, that was a very large annexation of land around Chicago. Not all the land that's in the lighter gray, but a large portion of it, especially northwest of the city of Chicago, was annexed. Most of Jefferson Township got pulled into the city, and the location of that village of Jefferson within Jefferson Township became what is known as Jefferson Park and is now a neighborhood of the city. So all of that together, that is why it is kind of widely considered that this is the first tornado in Chicago history. And as you, I guess just to illustrate this point is, this one article has spread into numerous sources. So we have National Weather Service records that talk about this happening in Norwood Park. We've got weather blogs that even put it on a map, despite the fact it doesn't provide a lot of precise location details. We've had maps online and blogs. Tom Skilling has a column, for the Chicago Tribune and also for WGN, where he talks about old tornadoes, and he's mentioned it at that location. So as you can see, this has spread everywhere despite not having a lot of precise details. Before I move on, I just want to talk a little bit about the weather conditions. We did take some time to dig into, what little was available just to see what the mechanism might have been, to cause the storm. Not very much is known. Official weather maps for the Signal Service, which became the Weather Service, didn't start until 1871. So this was, pre weather maps that you can just easily pull off of a server somewhere that have been digitized. But there are some limited reports of weather from volunteer observers that reported to the Smithsonian, and those were digitized by NCEI as part of what they call the Forts archive, or the Forts project, because most of them were military forts, but some of them were just farmers out in the country that decided to volunteer taking daily weather observations. We retrieved records for 30 such sites across the Midwest where the information was available. Typically, temperature, dew point, cloud cover, and wind speed would be available. Sometimes some remarks written off to the right, but those were the primary pieces of information that we could pull from these manual logs. They were digitized manually and put into an Excel spreadsheet. and then extracted at specific times, you know, like 7 a.m. on this day and 2 p.m. on this day, assigned to the lat long location of that town, and then we could put them on a map. So here's an example, the morning of the tornado, temperatures in the 70s, and you can kind of maybe piece together that there's maybe a warm front in northeast Iowa extending northeast from an area of low pressure. You know, with limited data, it's hard to say for certain, but possibly an area of low pressure there. And notice that in Illinois, I mean, we're starting the day with really warm temperatures and south winds potentially already pushing 80 in north central Illinois. By the afternoon, so this would be just a few hours before the tornado occurred, we were pushing the mid 90s in north central Illinois. Dubuque, near the corner of Illinois, Wisconsin, and Iowa, was at 99, which actually stood as their warmest May temperature on record until the 1930s in the Dust Bowl. And potentially that area of low pressure is probably moving to the east towards the Mississippi River, and possibly a lake breeze coming in off Lake Michigan, noted by the big difference in temperature. Like one county away from the lake in Wisconsin, we're at 90, but along the lakefront, we're at 69 with an east wind. And then by the late evenings, this was 9 p.m., several hours after the tornado, the lake breeze probably had moved a little further inland, but still good strong southwest winds in the interior of Illinois and that cold front nearing the river. So we know even from just newspaper reports, anecdotally, we know there was very hot and humid conditions in Illinois, even into southern Wisconsin. You know, possibly this lake breeze, it's really hard to be certain, but it's at least, there's some evidence suggesting that it could have been there. And we do know that lake breezes can at times, in certain situations, be a mechanism to produce storms along the western Great Lakes. So some new research into the tornado starting a few years ago. We decided to do, you know, another review of this tornado specifically to see if there was just any more detail we could find to help us narrow down the location. One of the things that really helped us is we recently discovered that many old newspaper articles had recently been digitized by the Library of Congress. It's a project that they called Chronicling America. And newspapers from all over the country back into the early to mid 1800s are available. Just for you to, you can even search. They have a, you know, like an AI routine that's scanned the text, and so it is a searchable text. Not always the best, but it gets, you know, a lot of the words pretty close. And also, you know, I mean, it's just all like you can just skim through the pages, just looking at the screenshots. It's really handy. So if you're doing any other historical research, this might be a good place to try. Also, there were old maps at the Library of Congress. I should point that out as well, too. So many old maps of counties, cities, states, even back into the late 1700s are available on the Library of Congress. So some clues that we took from that Chicago Tribune article to see if we could find other, you know, other things to expand upon. You know, it talked about just one house being destroyed. It only mentioned one name, the last name Page. Talked about the township of Jefferson. It talked about very large hail, which also extended to the southeast, eventually reaching Chicago. The storm moved from northwest to southeast. And that was pretty much it. And luckily, with doing some searches on the Library of Congress, however, we did find a few other newspapers that talked about the tornado. Unfortunately, none of the Chicago newspapers have been digitized in that archive, Chronicling America, but we did find Ottawa Free Trader, which was published kind of in north central Illinois, and some articles in New York actually picked up the story from local papers. So we did find some name discrepancies. Some of the articles talked about an H page, so provided a first initial. There also was a completely different name. R.L. Wheeler was mentioned as someone who owned a home that was hit by the tornado. One of the victims that died was mentioned by the last name Gillette. And then we started getting some different names of towns. So not only did we get town of Jefferson and Jefferson Mills once again, but we started hearing town of Maine and 1 mile distance from a notable railroad, one of the first railroads built to the northwest out of Chicago. So then that led us to property maps. We decided we'd look at property maps from the 1860s and see if we can find the name Page or the name Wheeler near Jefferson Township. Well, it turns out we couldn't find any properties matching those names. But if we were to look in Maine Township, which is a location where some of the other articles mentioned the location of the tornado, and we were to line up 1 mile distance from the railroad and a 16-mile distance from the city, they actually lined up much better than Jefferson Township. And if we look at property maps there, focusing on, again, that location, that 1 mile distance from the railroad and the 16-mile distance from Chicago, turns out very close to the western X of where those two overlap. Not only did we find a Jefferson property, but we also found a Wheeler property. And one of the dots in the middle of the Jefferson property indicated there was a mill, along the river within their property. So certainly a very strong clue that perhaps the most widely used newspaper source just had the wrong township, and it really was in a different location entirely. Decided that we needed a little further confirmation, so we took a trip to the main library in Chicago to review microfilm of newspapers that published in the 1850s. It turns out that of the 4 newspapers publishing at the time, 3 of the newspapers were available on microfilm. And in reviewing those, we found out that actually the only newspaper that talked about this tornado happening in Jefferson Township was the Chicago Tribune, and every other newspaper said that it happened in Maine Township. So just kind of I guess some bad luck that the one newspaper that is the easiest to get your hands on, and not have to go to microfilm at a library, it turns out that one newspaper is the one that got the location wrong. For even further corroboration, we decided to use the free resource Family Search, which is similar to Ancestry.com, to see if there's any genealogical records that could help piece together what happened. Turns out that there was census records in 1860 that mentioned the name R.L. Wheeler and had many individuals living in the same home, all with the last name Page. And this was in Maine Township, now the new hypothesis of where the tornado location was. We also were able to find on the big consensus family tree on Family Search that the R.L. Wheeler was married to an individual named Sarah Maria Page, who was the daughter of Joseph Page and Samantha Page. And Samantha's date was, interestingly enough, indicated as May 22nd, 1855. So think back in those times, there was only like 700 people living in that township, and to have someone die at the date of the tornado is kind of another interesting potential clue. Another thing we noticed is that they had numerous children, each of which were born about 2 years apart, but there was a notable gap between 1851 and 1855. So our hypothesis at the time was that if someone had constructed this family tree based upon census records, any child born after the 1850 census but died before the 1860 census would not have been listed in that family tree. Luckily, we had one other source on Family Search. They have what's called their pedigree resource file, which is just anonymous family tree snippets that people can submit. And they aren't that big consensus family tree that goes all the way, back into the 1400s and, to modern times that people build while they're doing their genealogy. These are just little snippets like, oh, I found something in, family records that talks about these people in the 1700s, and it might only have 2 or 3 generations, and they're just little snippets, out in the web of your family's past. Turns out that we found a hit for this family as well in those anonymous, at least submitted family histories. And in one of those, there were 2 additional children listed for Ransom and Sarah, both of which died on May 22nd, 1855, one of which was a child who was born that spring and only lived for 3 months. So then we decided to turn to the local history center. The town of Des Plaines is in Maine Township, and when we reached out to their historical society, it turns out that they were able to corroborate the vast majority of the things we found in the newspaper and in genealogical records. In fact, it turns out that some people had submitted old family histories to their center. They found them in their archives after we reached out to them, basically saying the same thing, that that the many members of the Page and Wheeler family were killed by this tornado on May 22nd, 1855, 2 of which were very young children. So we were able to build a family tree and show the individuals that were injured, the people that had passed away. It turns out there was like 10 people in this house when it was lofted off of its granite foundation. and almost every single person in the house was injured. Several people killed, the 2 small children, the grandparent, and a visiting aunt from New York State who just happened to be, visiting at the time. And interestingly enough, and Brett told me to bring this up, is it seems like every single person that I've researched associated with this story is semi-related to me in some way, which is kind of interesting that I didn't even realize. Family Search says that like almost every single person, like witnesses of the tornado, the family, are either 6th or 7th cousins, back into like the 1700s, where I was able to find a common ancestor. So kind of an interesting little tidbit I found while I was doing this. So we have been able to revise the account based upon all available information. We believe that there was a storm track somewhere from Maine Township southeast to the city of Chicago. In addition to what I presented here, we did find other reports of hail, around the area of the tornado, and hail in Chicago. So we have a very approximate corridor that we believe the storm moved from roughly 3 p.m. to 4 p.m. on May 22nd. We also believe that, we have this approximate tornado track, which now now is believed to have occurred in the village of Des Plaines, near the modern day intersection of Lee Street and Oakton Street, now the location of a drive-through bank on Oakton Street. And as you might imagine, Des Plaines is not the city of Chicago, so it did not happen where it previously was believed. Now, for more details, we have a couple places you can go if you want the technical side of things. We have an article that we published in BAMS. And for the kind of more the story side of things, there is an online story map. You can get to it if you just Google Des Plaines tornado of May 22nd, 1855. Since we published, however, we did find a few more pieces of information. It turns out there were letters written to the Smithsonian about the tornado, because it was one of the first that happened in northern Illinois. Also, some letters that were archived at the Des Plaines History Center. They have a backlog of letters they've been trying to transcribe. And while we were doing this, they happened to come across another letter written about the tornado by someone who was, like in his 70s and was writing to other family members and said, oh, back when I was a boy, I remember this tornado. And he gave pages of detail about how it moved and the directions that it changed, and about the hail and the family, the history of the family and how they were impacted by it. It turns out the tornado track is likely longer, so that map I showed you was from our publication, but we do have reason to believe the tornado track was longer, potentially making weird turns and maybe even changing direction entirely, like taking a 180. And also we believe the tornado was visible from almost every vantage, that even though the rain and hail happened about the same time, it wasn't heavy enough to obscure the tornado, because we do have some witnesses that were easily 4 miles away and were watching it while it was hailing. So there are still some remaining questions. However, the one that we, maybe not a huge question, but like, what's this confusion over Jefferson? Obviously there was that mill, the Jefferson mill, that showed up in the newspaper. It's possible that that family, the Jefferson family, they were so prominent in the area and built this prominent mill, and possibly even owned a general store near the mill. It's possible the reporter thought that was the town of Jefferson. It's along the same rail line. The last stop that they may have gotten off on the rail line was the Jefferson post office mail stop, the train stop. And they may have believed they still were in the same town. That's one possibility. And other than that, we can't say for certain, but that's the best we can come up with. We still don't know where any of the victims are buried. All the birth records, death records, property records, all that was lost in the Chicago fire of 1871. So we don't really know. And even all the information we found so far from the family, they say they don't know where they were buried. The only cemetery for, within a few miles of this did not really start having burials until a few years after the tornado. So the Des Plaines History Centers told us that before cemeteries were organized, oftentimes people buried their family members on their property. And at the time, this was farmland, and now it is a kind of a dense suburban area of the Chicago metro. So you can kind of read between the lines there. It's entirely possible that the victims of this tornado are still in someone's backyard. And as far as like the tornado's track, we have a couple different, there's the one we published, but there's a couple other possibilities based upon the descriptions. Hard to say for certain. We just know that it hit that farmhouse, near that one corner in Des Plaines. But the one at the far right, it was a very detailed description of how the tornado tracked. It basically curved upon itself and then turned back another direction, which is kind of interesting. I'd like to acknowledge the records stored at Family Search. Without the genealogies, that we wouldn't have been able to corroborate a lot of the information. Obviously, the Library of Congress was a big help, the digitized maps and newspapers. The staff at the Harold Washington Library in Chicago put up with me for the better part of an 8-hour day, constantly asking them for more reels of microfilm, and they had to go back in the stacks and dig these out. So, a big help to them while I was sitting there drinking my coffee and reading old newspapers. Des Plaines History Center was a big partner on this, as well as the descendants of the family who just happen to have, letters and other information about their descendants and those oral histories that they were able to share that helped piece this all together. And thanks to Brett, who, if it wasn't for him as a co-author telling me that I needed to publish this, it would have just been a little footnote in our Chicago Weather Service archive. So thanks to him for pushing me along the way to publish in BAMS. And I thought this might be an interesting slide to add. I didn't present this at the, when I last presented this at the GIS Association conference, but just maybe some lessons learned. If someone else is thinking of doing this at their office, really start with the Library of Congress, because you might find, even if a local newspaper is not archived there, newspapers back in the 1800s tended to pick up each other's stories. And I found out that the way that they did this, there was not really a newswire service back then. And even though telegraph existed in the mid 1850s, it cost like $10 to send a 1 or 2 sentence telegraph. At least that's from what I read. It didn't get cheaper until a few decades later. And so really they were not, using telegraph to share news, at least not whole stories. What they were doing is one newspaper would subscribe to another newspaper. So like the Chicago Tribune might be a subscriber to the New York Herald. And then it got sent via postal mail. And the Chicago Tribune would then publish some of the big articles from New York. And that's probably what you might find. If you're trying to look at an old event, you might find articles published in places you wouldn't expect. And it might say like from the such and such, Tribune, and it be for the event you're looking at. If that doesn't help you, you might have to go find the local library kind of closest to where it happened and dig through microfilm. But and you also have the possibility to look at genealogical records. But I should point out that we had a really good match with this event, and I've tried going the genealogy route with a few other tornadoes, and it's not helped as much. So we did kind of luck out that we got so much information from the genealogy for this particular tornado. It might help you, but it might also, you might end up with a dead end if those families just don't share, the detailed information that we found from the Page and Wheeler family. So that is all I have, and would be interested in people's questions.
All right, well, thank you, Scott. That was fascinating. Like really interesting stuff. So if anybody has any questions, please throw your hand up and I can unmute you to ask Scott some questions. So I'm waiting here. Scott, how did you happen to realize that these folks were long-range relatives of yours?
Well, it was surprisingly easy, actually. So when you're using Family Search, which I have an account on, and again, like I said, it's free, but you do have to have a sign up with an email address. There's a button. You pick any person in this giant, the big consensus family tree. And once you're looking at that person's page, there's a button that says, "How am I related?" And when you click that, it'll do that little, the calculation. And not just the Page and Wheeler family, I clicked and it said that I was 7th cousins. Beyond what I've presented here, I've looked at all kinds of eyewitness accounts from people who had totally different last names, lived in different rural areas around the storm. And the vast majority of them, I found out I'm either 6th or 7th cousins, which is really interesting. And it's always on my mother's side. So someone who's a genealogist and smarter with that, maybe will tell me, oh, it's, very common to be 6th cousins with any person in the world. It's like 6 degrees of Kevin Bacon or something. But I thought that was still at least somewhat rare, especially to have it happen over and over and over. I mean, it's like 6 different people associated with the story that it seem unrelated the way that the story is told back then, but then turns out, I'm related. So I don't know.
Yeah, that's just crazy. All right, so we had a question from Todd Krause. It says, what entry, if any, is there in Tom Grazulis's book?
I have to try to remember. I think that his is similar to what went into the, I believe it's Finley, who wrote the signal service paper back in the late 1800s and basically documented all the known tornadoes up to that point. And I believe it says the same thing, that just that there was a tornado in Cook County near Jefferson. I'd have to go pull it off the shelf because that was one of the first things we looked at like really early on, and I can't remember the exact entry, but I do remember that I don't think it was correct. That I believe he probably used the Chicago Tribune because that's what you can access like on newspapers.com. It's easy to find. And it's, you know, a lot of these other newspapers too, I guess I didn't point this out. Several of those other newspapers eventually merged with other newspapers, which eventually merged with the Tribune. So like the one newspaper at the time that provided some of the most detail and put it in the right place, the Chicago Democratic Press, not just like 2 or 3 years after this tornado, they merged with the Chicago Tribune. So there's a lot of that kind of stuff, and it's hard then, you know, to find the archives because even though the Tribune bought them out, they didn't archive the Democratic Press for some reason, and you don't find it on the newspapers.com to my knowledge. So I think it was, you know, in the right county, but in the wrong place.
All right, so any additional questions from anyone here? I'll give it a minute or so. Otherwise, this is, again, this great, Scott, some good information for maybe any other office who would go through this process to use as a resource, and it's recorded, so we'll be able to share with everybody now. So, all right, I'm not seeing any other questions, so I guess with that, I will let everyone have the rest of their day back. So thanks again for joining, everyone. Thank you to our presenters. It was a great guest speaker series today. So have a great one. Thanks.